So here's a big question. What if we could build our digital worlds on a foundation that was mathematically provable, to be honest? Not just secure, but provably honest. Well, that's really the core idea behind the TetraKlein architecture. Today, we're going to break down how this unified computational substrate was designed and, more importantly, how it was validated against the hard constraints of reality.
And this right here, this is the fundamental question that the architects of this system posed. This isn't just some academic thought experiment, it's a direct challenge to unify what we normally see as completely separate, highly complex fields, things like post-quantum cryptography and extended reality physics, and bring them all into a single, coherent, and crucially, verifiable whole. Answering this question is pretty much the entire purpose of this project, and it's going to be our guidepost for this whole explainer.
It's worth noting that the work we're looking at comes from Bar-MI Station Research, which is an independent, nonprofit lab. Now, this context is actually pretty important. It really frames the project's goals as purely foundational research, free from the typical pressures of commercial development.
All right, here's how we're going to break this down. First, we'll start with the high-level vision. What is this system even trying to achieve? Then, we'll get into the weeds a bit and define the core technical building blocks. After that, we'll see how those blocks actually held up under a series of stress tests. We'll analyze the performance data, and finally, we'll talk about what it really means to ground a complex architecture like this in physical reality.
So, let's kick things off with that core vision. Look, as our digital and physical lives continue to merge, the infrastructure they're built on becomes absolutely critical. The goal of TetraKlein is to create a foundation for that future infrastructure that isn't just secure, but can be mathematically proven to be honest, right from the ground up.
Now, to pull this off, TetraKlein has to synthesize work from a pretty formidable set of disciplines. We're talking about post-quantum cryptography, right? For security that can actually resist attacks from future quantum computers. Then you've got zero-knowledge proof systems, which let you prove a computation was done correctly without revealing any of the underlying data. This relies on things like deterministic virtual machines, physics modeling for extended reality, and synchronization frameworks for digital twins. And to top it all off, it's all built on a distributed ledger using something called hypercube blockchain-based mathematics. Each of these is a whole world unto itself. TetraKlein's ambitious goal is to make them all speak a single, unified, verifiable language.
And here it is, the long-term vision laid out plain and simple. It's all about building the foundation for fully immersive, extended reality worlds. Worlds where the digital simulation, the digital twin, is provably and continuously synchronized with our physical reality. We're talking about a future where digital trust isn't an afterthought or some add-on feature. It's a fundamental mathematical guarantee of the system itself.
Okay, so how do you even begin to build, let alone validate, a system this ambitious? Well, it all starts with defining the conceptual building blocks. To really get what's happening in the validation phase, we first need to get a handle on these core primitives that everything else relies on.
First up, we have the algebraic intermediate representation, or AIR. The best way to think of AIR is as the universal physics engine for the entire system, but it's written in the language of mathematics, specifically low-degree polynomials. Every single valid action the system can take, from a tiny calculation to a really complex interaction, must obey these mathematical rules. This strict algebraic rulebook is what allows the entire system's behavior to be proven using what are called STARKs, which stands for Scalable Transparent Arguments of Knowledge.
Next is something called incremental verifiable computation, or IVC. This is a really powerful cryptographic technique for recursion. So imagine you have a whole year's worth of computations. Instead of rechecking every single step from the beginning, IVC lets you create a single compact proof that attests to the validity of the entire chain. Each new proof essentially folds in or absorbs the validity of all the previous ones. Honestly, without this, verifying the system's history would be just impossibly slow and expensive.
Now, underpinning those Stark proofs is the FRI protocol, which stands for Fast Reed-Solomon Interactive Oracle Proofs. Okay, so if AR is the rulebook, then FRI is the referee. Its whole job is to efficiently check that the system's actual computational history, its trace, truly followed those polynomial rules laid out in the AR. It's really the core cryptographic engine that gives Starks their power and their integrity.
For the distributed ledger part, TetraKlein uses what's called a hypercube blockchain base, or HBB. So instead of organizing blocks in a simple linear chain like you see in traditional blockchains, the network is actually structured as a mathematical hypercube. This topology gives it incredibly high connectivity, which ensures that information spreads through the entire network with maximum efficiency.
and that's absolutely essential for maintaining a consistent global state across all the nodes.
Now, this next part is how the system actually connects back to the real world. It's called Digital Twin Convergence, or DTC, and it's the set of mathematical laws that bind the simulation to reality. It's a contractive framework, which means it actively pulls the digital twin back into alignment with its physical counterpart, making sure any divergence is always bounded and corrected.
And finally, to maintain a tamper-evident history, the system uses Recursive Tesseract Hashing, or RTH. This is a really unique multidimensional hashing scheme that creates what the architects call an entropy lineage. What it does is provide a verifiable, chronologically sound record of all system events, ensuring that the history of what happened and in what order cannot be secretly changed.
Okay, so now that we've got the building blocks, we can move to the real core of this explainer, the validation gauntlet. This is where we get to look at the empirical evidence from stress tests that were run not on some exotic supercomputer, but on accessible, everyday consumer-grade hardware.
The first and maybe the most critical validation goal was to test the stability of that incremental verifiable computation folding process we talked about. Because if this process were to expand or become unstable with each recursive step, the entire system would just be computationally infeasible. Game over.
This slide shows the direct output from the test log, and the key number you want to look at is right here, the residual after folding. After 40 recursive steps, that value is incredibly close to 0. And that tiny number, that's exactly what you want to see. It proves the process is contractive. It actually shrinks and stabilizes with each step, instead of growing uncontrollably.
So the verdict from this test is completely unambiguous. The core recursive proof mechanism is stable. It's not going to spiral into some computationally expensive mess, which is a fundamental prerequisite for building any practical system on top of it. Check.
All right, the next validation goal targets the network topology itself. The test needed to confirm that the hypercube blockchain base has the right mathematical properties, specifically something called its spectral gap, which dictates how quickly information can mix across the entire network.
So here we're seeing the log data for hypercubes of dimension 32 and 64. The crucial point here is that the measured spectral gap in the gap column perfectly matches the theoretical expectation in the expected column. And this isn't just some abstract check, it's a direct verification that the network will behave exactly as designed, which ensures rapid consensus and state consistency.
So the conclusion is crystal clear. The HBB network structure is mathematically sound, and it scales exactly as predicted by theory. This gives us a really strong foundation of trust in the system's distributed communication layer.
The next test tackles a potential hidden danger inside the system's rulebook, the AR constraints. See, when you combine multiple mathematical rules, there's a risk that their combined complexity, what's called the polynomial's degree, could just explode, which would make generating proofs computationally impossible. This test is all about making sure that doesn't happen.
And the results show that for a typical composition of constraints, the total degree is only 3. That is a very, very low number, well within the safety bounds needed for an efficient Stark proof system. So there's no degree explosion to worry about here.
And so this validation confirms another critical design property. The system's rules can be safely combined without creating some intractable mathematical problem, which ensures the entire architecture stays both provable and efficient. Another big checkmark.
The final validation goal in this section is a really practical one. Just a raw stress test. Can the system actually run under a sustained load on consumer hardware without crashing or spitting out errors?
The test was run on a capable machine, but it's fundamentally consumer grade. We're looking at an RTX 2070 Super and a Ryzen 7 CPU. I mean, these are components you could find in any modern gaming PC, which makes these results particularly relevant and really accessible.
And the result? A simple, declarative, OK. The GPU sustains the computational load without any errors. This is really the final piece of the puzzle in this section, demonstrating practical viability and closing that loop between abstract cryptographic design and real-world execution.
Okay, so passing the validation gauntlet is one thing, but what does it actually mean for performance? In this next section, we're going to analyze the concrete metrics from those tests to really understand the system's actual computational cost. This table is incredibly revealing. It shows how the cost for a verifier scales as the depth of that IVC recursion increases. Just look at the numbers.
At a depth of 64 recursive steps, the verifier's memory state is less than 1/100th of a gigabyte, and the number of operations is only in the thousands. This is logarithmic scaling, not the exponential explosion that would make a system like this totally impossible.
So the crucial engineering conclusion here is this. Incremental verifiable computation is absolutely feasible for deep recursion, even on consumer hardware. The cost of trust does not grow uncontrollably. Now let's look at the FRI protocol's performance. This table does a great job of illustrating the trade-off between cryptographic security, which is called soundness, the number of queries, and the verifier's cost and latency. You can see that as you increase the number of queries, the soundness, that is, the security against forgery, grows exponentially, while the cost in operations and latency only grows linearly.
But let's focus on the real-world impact of that final number. Even at 64 queries, which provides just an astronomical level of security against forgery, the verifier latency is only 0.018 milliseconds. That is blazing fast. It's fast enough for virtually any real-time application you can think of, including the super high-frequency demands of extended reality. So to summarize the whole performance analysis, these are really the key takeaways for any systems architect out there. Proof generation is fast enough for real-time batching. The energy cost is predictable. The entire model is suitable for aggregating data at the high frame rates that XR requires. And most importantly, this is not just theory. It runs, today, on standard consumer hardware.
All right, so we've seen the vision, we've defined the primitives, and we've walked through the successful validation and the performance tests. This brings us to our final section. What is the ultimate significance of all these findings, and what's the path forward from here?
This quote, and this is taken directly from the signed validation report, it just says it all. The work has successfully demonstrated that the execution model isn't some cryptographic curiosity, it is grounded in physical reality. It bridges that often vast gap between an elegant design on paper and the messy constraints of real-world hardware.
The core thesis has been tested, and it's been confirmed. What these results do is illuminate a credible pathway toward a truly unified computational substrate, one that is both rigorously verifiable through mathematics and, as we've just seen, computationally feasible on hardware that people actually have.
And so we end right where we began, but with a whole new perspective. The initial research asked if we could even design such a system. The validation work strongly suggests that, yes, we can. So the new question, the one this work leaves for all of us to consider, is this. What becomes possible when the digital worlds we build are, by their very nature, provably honest?